Have you ever wondered what secrets the universe is hiding? Imagine stars so massive they could swallow our solar system, planets where it rains molten glass, and black holes that can trap light itself. Discover galaxies colliding in slow motion, invisible forces shaping reality, and mysteries so strange they'll leave you questioning everything you know. Join me as we explore them. The creation of space. Space is not a passage void, but a dynamic, evolving entity that has shaped everything we observe, from galaxies and stars to the fundamental structure of reality itself. Understanding how space came into being requires exploring the intersection of physics, cosmology, and philosophical inquiry. It is a journey into the very foundation of existence. The origin of space is tied to the Big Bang Theory, which describes the beginning of the universe approximately 13.8 billion years ago. At the Big Bang, space, time, energy, and matter were created in a singular, incomprehensibly dense, and hot state. However, the term bang is somewhat misleading. It wasn't an explosion in pre-existing space, but the simultaneous emergence and expansion of space itself. To grasp this concept, we must move beyond everyday intuition about space as a static, unchanging backdrop. Space is fundamentally intertwined with time, forming a unified fabric known as space-time, as described by Einstein's general theory of relativity. Before the Big Bang, the notion of space or time as we understand it didn't exist. The laws of physics, including the framework of cause and effect, break down as we approach the singularity, an infinitely dense point from which the universe expanded. Asking what came before the Big Bang is problematic, because time itself began with the event. Without time, the question of before loses its meaning, much as one cannot speak of north of the North Pole. At the moment of the Big Bang, space began as an almost infinitesimal region and expanded rapidly. This expansion is not matter moving into a pre-existing void, but the stretching of the space-time fabric itself. To visualize this, cosmologists often use the analogy of a balloon being inflated, where points on the balloon's surface represent galaxies moving apart as space expands. The surface of the balloon grows, but there is no inside or outside. The balloon, space itself, is all-encompassing. A critical aspect of the early universe was a phenomenon called cosmic inflation, which occurred in the first fractions of a second after the Big Bang. During inflation, space expanded exponentially, increasing in size by a factor of at least 100 septillion in an unimaginably short time. This rapid expansion smoothed out irregularities in the universe, creating the nearly uniform space-time fabric we observe today. Inflation also amplified quantum fluctuations, tiny random variations in the energy density of space, which later became the seeds for the formation of galaxies and cosmic structures. One of the most intriguing aspects of space is that it is not an empty void. Quantum field theory reveals that even the vacuum of space is teeming with activity. Space, at its most fundamental level, is filled with quantum fluctuations, where particles and antiparticles briefly pop into existence and annihilate each other. This quantum foam underpins the fabric of space-time, hinting at a deeper, more complex reality beneath the apparent smoothness of the cosmos. These fluctuations may have played a pivotal role during inflation, as their magnification could explain the clumpy distribution of matter we observe in the universe today. Einstein's theory of relativity revolutionized our understanding of space by showing that it is not a rigid framework, but a malleable fabric influenced by mass and energy. Massive objects like stars and galaxies warp space-time around them, creating what we perceive as gravity. These distortions allow light to bend in time to slow near massive objects, phenomena that have been observed in events like gravitational lensing and time dilation near black holes. Space is not passive. It is shaped and reshaped by the entities it contains. The creation of space is also deeply linked to the concept of the cosmological constant, a term Einstein introduced in his equations to describe the energy density of empty space. Initially thought to be an error, the cosmological constant has gained renewed significance in explaining the accelerated expansion of the universe, attributed to dark energy. Dark energy, a mysterious force permeating all of space. pushes galaxies apart at an ever-increasing rate. This suggests that space is not merely a stage for cosmic events, but an active participant in the universe's evolution. The cosmic microwave background, CMB, radiation provides a window into the early universe and the creation of space. This faint glow, detected in all directions, is the afterglow of the Big Bang, a relic of the moment when the universe became transparent as photons decoupled from matter. The CMB reveals a snapshot of the universe when it was just 380,000 years old, showing a nearly uniform distribution of energy with slight variations. These variations correspond to regions of slightly different densities, shaped by quantum fluctuations during inflation. The CMB confirms that space has been expanding and evolving since its inception, offering critical insights into its origins. The creation of space raises profound questions about its underlying nature. What, if anything, lies beneath space-time? Some theories, like string theory, suggest that space may emerge from more fundamental structures, such as vibrating strings or networks of quantum states. In these models, the space we experience is a higher dimensional construct, and the familiar three dimensions of space and one of time are merely emergent properties of deeper, multi-dimensional phenomena. The multiverse hypothesis takes this idea further, proposing that our universe is just one of countless others, each with its own version of space-time. If true, the creation of space in our universe might be just one instance in an infinite series of cosmic births, each governed by different physical laws. These ideas are speculative but offer intriguing possibilities for understanding the origins of space in a broader context. Another perspective comes from loop quantum gravity, which suggests that space is not continuous, but composed of discrete, finite units, much like pixels on a screen. According to this theory, space-time at the Planck scale, the smallest measurable scale, is quantized, consisting of tiny indivisible units. This idea challenges the classical notion of smooth space and opens the door to a radically different view of its creation and structure. The creation of space also involves philosophical considerations. If space and time emerge from the Big Bang, what does this imply about the nature of existence itself? Is space a fundamental aspect of reality, or is it a construct that arises from more basic principles? These questions push the boundaries of human understanding, requiring both scientific exploration and metaphysical reflection. Starquakes. Stars may seem like static points of light in the night sky, but in reality, they are dynamic, ever-changing objects. One of the most fascinating phenomena occurring within them is something called a starquake. These are oscillations or vibrations that ripple through a star's interior, somewhat akin to earthquakes on Earth, though on a scale that's difficult to fathom. To understand starquakes, imagine dropping a pebble into a still pond. The ripples that spread out across the water are similar to the waves traveling through a star. When a starquake occurs, these waves can reveal incredible details about the star's inner workings, making starquakes one of the most intriguing tools for studying stars. A starquake happens because of shifts in the star's internal structure. Deep inside a star, forces are constantly battling for equilibrium. Gravity is pulling the star's material inward, while the pressure from nuclear fusion at the core pushes outward. If something disrupts this balance, say a sudden change in the core's temperature or density, the star can experience a quake. The result is a series of oscillations that can last for hours or even days, depending on the size and structure of the star. These oscillations aren't visible to the naked eye, but they can be detected by studying the star's light. As the surface of the star ripples, the light it emits changes ever so slightly, almost like the way the tone of a bell changes when it vibrates. By carefully analyzing these tiny variations, astronomers can determine the frequency and amplitude of the star's oscillations. This field of study is called astroseismology, and it has revolutionized our understanding of stars. One of the key discoveries made through astroseismology is that starquakes provide a direct window into a star's interior. Normally, we can only observe the outer layers of a star, the photosphere, where its light is emitted. But astroseismology allows scientists to probe the hidden layers beneath, much like a doctor uses an ultrasound to see inside the human body. For example, by studying the oscillations of red giants, astronomers have learned how their cores are structured and how energy flows from the core to the surface. This information helps refine models of stellar evolution, giving us a clearer picture of how stars age and die. The study of starquakes has also shed light on the composition of stars. Different elements within a star's core create distinct oscillation patterns, much like different materials produce unique sounds when struck. By analyzing these patterns, astronomers can determine the ratios of hydrogen, helium, and heavier elements within a star. This is particularly valuable for understanding the early stages of a star's life, as well as its eventual fate. One of the most striking examples of astroseismology in action came from NASA's Kepler mission, originally designed to search for exoplanets. Kepler also monitored the light of thousands of stars, capturing data on their oscillations. This data has been a treasure trove for astroseismologists. For instance, scientists discovered that some stars exhibit solar-like oscillations, which are caused by convection currents in their outer layers. These oscillations are remarkably similar to those observed in our own sun, providing a fascinating point of comparison. Starquakes also reveal how magnetic fields influence stars. Stars' magnetic fields can alter the way waves travel through a star, creating unique patterns in its oscillations. This has important implications for understanding stellar magnetism, which plays a crucial role in phenomena like solar flares and coronal mass ejections. These magnetic events can have significant effects on nearby planets, including Earth. So studying them is vital for understanding space weather and its potential impact on our technology. In addition to improving our understanding of individual stars, starquake data has broader applications for astronomy as a whole. For example, by studying the oscillations of stars in different stages of their life cycles, astronomers can refine models of stellar evolution. These models are essential for predicting how stars of various sizes and compositions will behave over time. They also help us understand the origins of elements in the universe, as different types of stars produce different elements through nuclear fusion. The impact of starquakes isn't limited to theoretical models. They also have practical applications for understanding the cosmos. For instance, astroseismology has been used to determine the ages of stars with remarkable precision. Knowing a star's age is crucial for understanding the history of its planetary system. In some cases, this information can even shed light on the potential for life on planets orbiting that star. If a star is too young, its planets may still be forming. If it's too old, its planets may no longer be habitable. Starquakes help us pinpoint where a star falls on this timeline. Another exciting area of research involves studying starquakes in massive stars, which can offer clues about their eventual fates. Massive stars often end their lives in dramatic supernova explosions, leaving behind neutron stars or black holes. By analyzing the oscillations of these stars, scientists can learn more about the conditions leading up to these explosions. This, in turn, helps us understand the role of massive stars in shaping galaxies and seeding the universe with heavy elements. Even neutron stars, the dense remnants of massive stars, can experience starquake-like phenomena. These are called crustquakes and occur when the rigid crust of a neutron star suddenly shifts. Studying crustquakes provides insights into the extreme conditions inside neutron stars, where matter is compressed to densities that defy our understanding of physics. Starquakes also have a poetic side. They remind us that stars are not static, lifeless objects, but dynamic, evolving systems. They are constantly changing, responding to the forces within and around them. This dynamic nature makes stars endlessly fascinating to study, as each new discovery reveals another layer of complexity. The birth of stars and the origins of planetary systems. Stars emerge from regions in space known as molecular clouds, vast stretches of gas and dust that are often scattered across galaxies. These clouds are immense, some of them spanning light years in diameter, and they serve as the cradles of stellar creation. Imagine looking at the wispy edges of a cloud on Earth, but instead of water vapor, these cosmic clouds are composed primarily of hydrogen, along with traces of helium and other elements. They drift quietly in space until something disrupts their balance. It could be a nearby supernova explosion, or even the gravitational influence of a passing star. When this happens, sections of the cloud begin to collapse under their own gravity. This collapse is the first step in star formation. As the gas falls inward, it heats up, and the center of the collapsing region forms what we call a protostar, a glowing, dense core that will eventually become a fully fledged star. To put this in perspective, think of squeezing a ball of clay. The more you compress it, the denser it becomes. In a protostar, the compression is so intense that the core reaches millions of degrees, hot enough for nuclear fusion to ignite. At this stage, hydrogen atoms are smashed together to form helium, releasing an enormous amount of energy. This energy provides an outward pressure that balances the inward pull of gravity, creating a stable star. Our sun went through this process billions of years ago. Surrounding this young star is a disk of leftover gas and dust known as a protoplanetary disk. These disks are fascinating because they are the starting point for planetary systems. Picture a spinning potter's wheel with clay being shaped into a bowl. In a similar way, particles in the protoplanetary disk collide and stick together, forming clumps that grow over time. These clumps become planetesimals, the building blocks of planets. Some of these planetesimals merge into full-size planets, while others become moons, asteroids, or comets. The conditions within the disk determine what kinds of planets form. Closer to the star, where temperatures are high, rocky planets like Earth and Mars take shape. Farther out, where it's colder, gas giants like Jupiter and Saturn can form with thick atmospheres of hydrogen and helium. This division between rocky and gas planets is why our solar system has such a diverse array of worlds. But the environment around a newborn star is anything but serene. Young stars emit powerful radiation and stellar winds, streams of charged particles that can blow away the surrounding gas and dust. These forces sculpt the planetary system, determining how much material is left for planets to grow. For example, the intense radiation from our sun likely cleared out much of the gas near its core, allowing Earth to form as a rocky planet rather than a gas giant. Observations of other stellar systems have revealed just how diverse planetary systems can be. Some stars have planets packed tightly together, orbiting in patterns that seem almost alien compared to our solar system. Others have planets on wide elliptical orbits that take them far from their stars. This diversity shows that the processes shaping planetary systems are both universal and highly variable, influenced by the unique conditions of each protoplanetary disk. One of the most exciting areas of research involves studying these disks directly. Using telescopes like ALMA, Atacama Large Millimeter/Submillimeter Array, scientists have captured images of young stars surrounded by disks with gaps and rings. These features are believed to be the footprints of forming planets, carving paths as they collect material. It's like watching a construction site where planets are the builders, and the protoplanetary disk is their raw material. Let's take a moment to consider how these processes played out in our own solar system around 4.6 billion years ago. The sun formed from a collapsing cloud of gas and dust within our galaxy. Surrounding it was a disk that eventually gave rise to planets, moons, and smaller objects. Over millions of years, gravity worked its magic, pulling particles together into larger and larger clumps. The inner part of the disk, rich in metals and silicates, formed the terrestrial planets: Mercury, Venus, Earth, and Mars. The outer part, where ice could remain solid, formed the gas giants and icy bodies like Pluto. The leftovers from this process didn't go to waste. Comets and asteroids, remnants of the early solar system, have provided scientists with a time capsule of its formation. By studying these objects, we've gained insights into the conditions that existed billions of years ago. Another intriguing aspect of planetary system formation is the role of migration. Early in their development, planets can change their orbits, moving closer to or farther from their stars. This migration can have dramatic effects on the entire system, pushing smaller planets into unstable orbits or even ejecting them into interstellar space. Our solar system shows signs of such migration. For instance, Jupiter's movements may have influenced the distribution of asteroids and the formation of the terrestrial planets. The study of exoplanets, planets outside our solar system, has added even more layers to our understanding. Some scientists have discovered planets that defy traditional models, such as hot Jupiters, gas giants orbiting scorchingly close to their stars. These discoveries challenge our ideas about how planets form and migrate, forcing us to refine our theories. Hypergiant stars. The life cycles of hypergiant stars and their explosive deaths. Hypergiant stars are rare, extraordinary objects that push the limits of what stars can be. These celestial behemoths are characterized by their immense mass and incredible luminosity, often shining millions of times brighter than the sun. Their sizes can stretch to hundreds or even thousands of times the sun's radius, making them among the largest stars in the universe. However, their brilliance comes at a cost. Hypergiants burn through their nuclear fuel at an astonishing rate, leading to incredibly short lifespans compared to stars like the sun. While our sun will exist for around 10 billion years, hypergiants last only a few million years, their lives ending in some of the most dramatic cosmic events known. To understand the life cycle of a hypergiant, it's essential to explore their formation. Like all stars, hypergiants form within molecular clouds, where dense regions collapse under gravity to create a protostar. However, what sets hypergiants apart is the sheer mass of the material they accumulate during this early stage. A hypergiant typically begins its life with a mass at least 30 times greater than that of the sun, though many exceed this, reaching hundreds of solar masses. This immense mass leads to core temperatures and pressures far beyond those of smaller stars, driving rapid nuclear fusion and producing the immense luminosity that defines them. From the moment a hypergiant ignites, it enters a turbulent existence. The fusion reactions generate immense radiation pressure, which counteracts the star's gravity, creating a precarious balance. This balance is far more unstable than in smaller stars, as the sheer weight of the outer layers pushes the core to extreme conditions. Over time, the star loses mass at an extraordinary rate through powerful stellar winds. These winds can carry away material equivalent to multiple Earth masses each year. The mass loss not only reduces the star's size, but also changes its chemical composition, exposing layers of heavier elements that were created through nuclear fusion. The instability of hypergiants is one of their defining characteristics. Their surfaces often exhibit dramatic pulsations, with the outer layers expanding and contracting in cycles. These pulsations can eject large amounts of material into space, creating vast, complex nebulae around the star. One famous example is Eta Carinae, a hypergiant surrounded by the Homunculus Nebula, a structure formed from massive outbursts during the star's life. Such outbursts are not just beautiful. They also indicate the violent processes occurring within the star as it approaches the end of its life. As a hypergiant nears the end of its short life, its core becomes increasingly unstable. The fusion of lighter elements like hydrogen and helium gradually gives way to the fusion of heavier elements such as carbon, oxygen, and silicon. Each stage of fusion occurs more quickly than the last, with the final stages lasting mere days or hours. The process culminates in the production of iron in the core. Unlike lighter elements, the fusion of iron does not release energy. Instead, it absorbs energy, causing the core to collapse under its immense gravity. This core collapse sets off a chain reaction that results in a supernova explosion. The outer layers of the star are blasted into space with incredible force, while the core itself is compressed to extreme densities. Depending on the mass of the core, it may become a neutron star or a black hole. Neutron stars, while incredibly dense, are composed almost entirely of neutrons and have diameters of only about 20 kilometers. Black holes, on the other hand, represent a point of no return in space-time, where gravity is so strong that nothing can escape. The supernova of a hypergiant is an event of immense significance in the universe. The explosion releases vast amounts of energy, momentarily outshining entire galaxies. It also produces a variety of heavy elements through a process called supernova nucleosynthesis. Elements like gold, uranium, and platinum are forged in these extreme conditions and then disperse into space, enriching the interstellar medium. Over time, these elements become part of new stars, planets, and even life forms, making hypergiants essential contributors to cosmic evolution. The remnants of hypergiant deaths leave behind fascinating phenomena. If the core collapses into a neutron star, it may become a pulsar, emitting beams of electromagnetic radiation as it rotates. If a black hole forms, it can become the center of a complex system, accreting material from nearby stars and generating high-energy emissions. In either case, the legacy of the hypergiant continues to influence its surroundings long after its death. Hypergiants also play a key role in shaping their galactic environments. The powerful stellar winds and supernova explosions associated with these stars can trigger the formation of new stars by compressing nearby molecular clouds. However, they can also disrupt star formation by dispersing gas and dust. This dual role as both creators and destroyers underscores the profound impact of hypergiants on the cosmos. Studying hypergiants is challenging because they are so rare and short-lived. Most of them are located far from Earth, and their extreme brightness often makes it difficult to observe their details. However, advances in telescopes and observational techniques have provided new insights. For example, infrared and radio telescopes can penetrate the dust surrounding hypergiants, revealing their structures and the interactions between their stellar winds and surrounding material. One of the enduring mysteries of hypergiants is why some of them explode as supernovae, while others appear to bypass the stage and collapse directly into black holes. The answer likely lies in the complex interplay of factors such as mass, rotation, magnetic fields, and the composition of the star. Understanding these processes is critical for refining models of stellar evolution and predicting the fates of massive stars. Another intriguing aspect of hypergiants is their variability. Many of these stars exhibit irregular changes in brightness caused by fluctuations in their outer layers. These variations can provide clues about the internal processes of the star, including the dynamics of energy transport and the role of convection. Observing these changes over time offers a glimpse into the tumultuous lives of these massive stars. The study of hypergiants also has broader implications for understanding the early universe. Massive stars like hypergiants were far more common in the early stages of cosmic history, when galaxies were forming and evolving. By studying these stars today, we can learn about the conditions that prevailed during that formative era, shedding light on the origins of galaxies and the chemical evolution of the universe. The existence of hypergiants challenges our understanding of stellar physics. Their sheer size and luminosity push the boundaries of what is possible for a star, forcing astronomy to refine its theories and develop new models. Each discovery about hypergiants adds a piece to the puzzle of how stars and galaxies evolve over billions of years. The creation of heavy elements through stellar nucleosynthesis. The universe began with only the simplest elements: hydrogen, helium, and traces of lithium. These primordial elements formed during the first few minutes after the Big Bang in a process known as Big Bang nucleosynthesis. Yet, when we look around today, we find a universe rich with a stunning variety of heavier elements: carbon, oxygen, iron, gold, and beyond. These elements, essential for the formation of planets and life itself, were forged within the hearts of stars through a process known as stellar nucleosynthesis. This intricate, multi-stage process reveals the remarkable power of stars as the cosmic forges of matter. At the core of every star, nuclear fusion is the engine driving its existence. Fusion occurs when the immense gravitational pressure at a star's core forces atomic nuclei to collide and combine. For a star like the Sun, this process begins with hydrogen, The extreme temperatures and pressures at the core overcome the natural repulsion between positively charged protons, allowing them to fuse into helium. This reaction releases energy in the form of light and heat, sustaining the star's radiance. For stars much larger than the Sun, the fusion process doesn't stop at helium. As these stars age, their cores grow hotter and denser, enabling the fusion of progressively heavier elements. Helium is fused into carbon, carbon into oxygen, and oxygen into neon, magnesium, and silicon. Each stage of fusion creates elements with higher atomic numbers, building up the periodic table within the star. These fusion reactions occur in layers, much like the layers of an onion, with the heaviest elements forming at the core. The fusion of lighter elements releases vast amounts of energy, which balances the inward pull of gravity and prevents the star from collapsing. However, this process has a limit. When the core begins producing iron, the star reaches a critical turning point. Unlike lighter elements, the fusion of iron absorbs energy instead of releasing it. This energy drain destabilizes the star, leading to its inevitable collapse and explosive death. The death of a massive star as a supernova is one of the most dramatic events in the cosmos, but it is also one of the most important for the creation of heavy elements. The intense heat and pressure generated during a supernova enable a process called rapid neutron capture, or the R process. In this process, atomic nuclei rapidly capture neutrons, creating extremely heavy and unstable isotopes. These isotopes decay into stable elements such as gold, platinum, and uranium. Without supernovae, these elements would be exceedingly rare, if they existed at all. Not all heavy elements are formed in such violent events. The slow neutron capture process, or the S process, occurs in stars during their later stages of life, particularly in asymptotic giant branch HB stars. These stars experience episodes of convection that bring material from their cores to their outer layers, where neutron capture occurs over thousands of years. The S process produces elements such as barium, strontium, and lead, which are then dispersed into space by stellar winds. The material ejected by dying stars enriches the interstellar medium, the vast expanse of gas and dust between stars. Over millions of years, this enriched material becomes part of new stars and planetary systems. Our solar system, for instance, formed from a cloud of gas and dust that had been seeded with heavy elements from previous generations of stars. The carbon in our bodies, the oxygen we breathe, and the calcium in our bones were all forged in stars long before the Earth existed. In some cases, heavy elements are produced in even more exotic environments. Neutron star mergers, for example, are among the most significant sources of R process elements. When two neutron stars collide, they create conditions so extreme that vast amounts of heavy elements are synthesized in moments. Observations of kilonovae luminous explosions resulting from such mergers have confirmed that these events produce elements like gold and platinum in quantities that dwarf the reserves found on Earth. The creation of heavy elements is also influenced by the mass and metallicity of stars. Metallicity, in astronomical terms, refers to the abundance of elements heavier than helium in a star. High metallicity stars, which formed later in the universe's history, have more complex fusion processes because they start with a greater variety of elements. In contrast, the first stars, known as Population 3 stars, were composed almost entirely of hydrogen and helium. These primordial stars were incredibly massive and short-lived, ending their lives in supernovae that seeded the universe with the first heavy elements. One of the challenges in understanding stellar nucleosynthesis lies in observing these processes directly. Much of what we know comes from studying the light emitted by stars. The spectral lines in a star's light reveal the presence of specific elements, allowing astronomers to determine its composition. For instance, the discovery of heavy elements in the spectra of distant stars has provided evidence for nucleosynthesis occurring across the universe's history. Another key area of research involves studying the remnants of supernovae. These remnants, such as the Crab Nebula, contain clues about the processes that occurred during the explosion. By analyzing the composition of these remnants, astronomers can trace the origins of specific elements and refine models of how they are produced. The implications of stellar nucleosynthesis extend far beyond the stars themselves. The elements forged in stars are the building blocks of everything we see around us. The water in our oceans, the silicon in our computer chips, and the iron in our blood all owe their existence to the life cycles of stars. Even elements like iodine, essential for human health, were created in supernovae and dispersed across the cosmos. In recent years, advancements in computational modeling have provided deeper insights into the complexities of nucleosynthesis. These models simulate the conditions within stars and during supernovae, allowing scientists to test theories about how elements are created. For example, simulations have revealed how variations in a star's rotation, magnetic field, and mass loss rates can influence the production of heavy elements. These models also help explain why certain elements are more abundant in some regions of the galaxy than others. This event was followed by observations of electromagnetic radiation across multiple wavelengths, providing an unprecedented opportunity to study the aftermath of a neutron-star merger. The visible and infrared light from the kilonova displayed a unique spectral signature, directly confirming the presence of our process elements. Gravitational waves play a critical role in our understanding of neutron-star mergers and kilonovae. These ripples in space-time carry information about the masses, spins, and orbital dynamics of the merging neutron stars. By analyzing the gravitational wave signals from events like GW170817, scientists can determine key properties of neutron stars, such as their maximum mass and the equation of state that governs their behavior. This information is essential for understanding the nature of dense matter, which cannot be replicated in any laboratory on Earth. Kilonovae also provide insights into the expansion of the universe. By combining data from gravitational waves and electromagnetic observations, astronomers can measure the distance to neutron-star mergers with remarkable precision. This makes kilonovae valuable standard sirens for determining the Hubble constant, a key parameter that describes the rate at which the universe is expanding. Resolving discrepancies in the Hubble constant measured by different methods is one of the most pressing challenges in modern cosmology, and kilonovae offer a promising new approach. The material ejected during a neutron-star merger is another area of intense study. This ejecta is highly anisotropic, meaning it is not distributed evenly in all directions. Some of it is launched at high speeds in jets, which can produce short gamma-ray bursts, intense flashes of gamma rays, lasting less than 2 seconds. These bursts are among the most energetic events in the universe, and their association with neutron-star mergers was confirmed by observations of GW170817. The slower-moving ejecta, on the other hand, forms the kilonova's visible light and infrared emission, which fades over days to weeks as the radioactive elements decay. The theoretical modeling of kilonovae is a complex endeavor involving simulations of hydrodynamics, nuclear physics, and radiative transfer. These models aim to predict the light curves and spectra of kilonovae based on the properties of the merging neutron stars and the conditions of the ejecta. Comparing these predictions with observations helps refine our understanding of the processes that drive kilonovae and the production of heavy elements. Beyond their scientific significance, kilonovae have profound implications for the broader cosmos. The heavy elements formed in these events are dispersed into the interstellar medium, where they become part of new stars, planets, and even life. The gold in your wedding ring and the platinum in your electronics were likely forged in a kilonova billions of years ago. This cosmic connection underscores the deep interdependence of life and the universe's most extreme phenomena. Kilonovae also raise intriguing questions about the frequency and distribution of neutron-star mergers. While these events are rare on cosmic timescales, they occur often enough to account for the observed abundance of heavy elements in the universe. By studying the rates of kilonovae in different types of galaxies, scientists can learn more about the formation and evolution of binary neutron star systems. One of the most exciting frontiers in kilonova research involves the use of next-generation observatories. The upcoming Vera Rubin Observatory, the James Webb Space Telescope, and improvements in gravitational wave detectors promise to expand our ability to detect and study these events. These instruments will allow astronomers to observe kilonovae at greater distances and with unprecedented detail, uncovering new insights into the physics of neutron-star mergers and the origins of heavy elements. The structure and mysteries of the interstellar medium. The interstellar medium, ISM, is a vast, complex expanse of matter and energy that fills the regions between stars within galaxies. Far from being empty, this medium is a dynamic and essential component of the cosmos, influencing everything from the birth of stars to the evolution of entire galaxies. Its composition, structure, and interactions hold keys to understanding both the grand-scale workings of the universe and the detailed processes occurring within galaxies like our own Milky Way. The ISM is primarily composed of gas, with hydrogen accounting for about 90% of its mass and helium making up most of the remainder. Trace amounts of heavier elements, what astronomers call metals, are also present, often in the form of molecules, ions, or solid dust grains. Dust grains, although they constitute only about 1% of the ISM's mass, play a disproportionately important role in many astrophysical processes. These tiny particles, typically made of silicates, carbon, or ices, absorb and scatter starlight, creating the beautiful nebulae visible in optical and infrared wavelengths. Cosmic rays, high-energy particles that originate from sources such as supernova explosions, are another critical component of the ISM. These particles travel at nearly the speed of light and interact with the gas and dust, contributing to the chemical and physical evolution of the medium. The interplay of cosmic rays with the ISM also produces gamma rays, which serve as a tracer for the high-energy processes occurring within galaxies. One of the most fascinating aspects of the ISM is its division into distinct phases, each characterized by different temperatures, densities, and physical conditions. These phases exist in a dynamic equilibrium, constantly exchanging matter and energy. The coldest and densest regions are molecular clouds, where temperatures can drop to just a few degrees above absolute zero and the density can reach hundreds or thousands of particles per cubic centimeter. These clouds are the birthplaces of stars, as gravity causes the gas and dust to collapse into dense cores, eventually igniting nuclear fusion. Warmer regions, known as diffuse atomic clouds, have temperatures of several thousand degrees and densities of about 1 particle per cubic centimeter. These regions are often ionized by ultraviolet radiation from nearby stars, creating HI regions, clouds of ionized hydrogen that glow brightly in optical wavelengths. The hottest and most diffuse phase of the ISM is the hot ionized medium, which is dominated by gas at temperatures of millions of degrees. This phase is created by shock waves from supernova explosions, which heat the gas to extreme temperatures and inject large amounts of energy into the ISM. The boundaries between these phases are not fixed. They shift and interact in response to events like supernovae, stellar winds, and galactic dynamics. For example, the shock waves from a supernova can compress nearby molecular clouds, triggering star formation. Conversely, these same shock waves can also disperse clouds, halting star formation in certain regions. One of the most striking features of black hole jets is their collimation, how tightly they are focused. Despite traveling enormous distances, these jets maintain remarkably narrow paths, indicating highly organized magnetic fields. However, the jets are not static structures. They are often observed to wobble or precess over time, a phenomenon that may result from the misalignment of the black hole spin axis with the accretion disk. This dynamic behavior creates complex interactions with the surrounding medium, generating shock waves and turbulence. The impact of black hole jets on their host galaxies is profound. These jets carry away significant amounts of energy and momentum, affecting the gas within the galaxy. In some cases, the energy from the jets heats the gas, preventing it from cooling and collapsing to form new stars, a process known as feedback. This feedback mechanism is particularly important in regulating the growth of massive galaxies, as it can suppress star formation and limit the accumulation of gas in the galactic core. Conversely, black hole jets can also trigger star formation under certain conditions. As the jets plow through the interstellar medium, they compress gas clouds, creating regions of high density where new stars can form. This dual role, both suppressing and stimulating star formation, underscores the complexity of jet feedback and its dependence on the specific conditions within a galaxy. The influence of black hole jets extends far beyond their host galaxies. Jets can inject energy and material into the intergalactic medium, IGM, the vast space between galaxies. This injection creates large-scale structures, such as radiolobes, enormous bubble-like regions filled with relativistic particles and magnetic fields. Observations of these structures, such as those associated with the galaxy M87, reveal jets stretching across hundreds of thousands of light years, shaping the IGM and redistributing energy on cosmic scales. Jets also play a crucial role in the evolution of galaxy clusters. In the dense environments of clusters, jets interact with a hot, diffuse gas known as the intercluster medium, ICM. The energy deposited by jets can create cavities or bubbles in the ICM, as seen in systems like the Perseus cluster. These bubbles rise through the ICM, redistributing heat and preventing runaway cooling that would otherwise lead to excessive star formation. This process, known as active galactic nucleus, AGN feedback, helps maintain the balance between heating and cooling in galaxy clusters. Observational evidence of black hole jets comes from a variety of wavelengths, each revealing different aspects of their nature. Radio observations, for example, are particularly effective at detecting synchrotron emissions from relativistic particles, allowing astronomers to map the structure of jets and their associated lobes. X-ray telescopes, on the other hand, capture the high-energy interactions between jets and their surroundings, including shock waves and hot gas. Gamma-ray observations provide insights into the most extreme processes occurring within jets, such as particle acceleration near the black hole. One of the most famous examples of a black hole jet is in the galaxy M87, located in the Virgo cluster. The jet from M87's supermassive black hole extends for about 5,000 light-years and is visible across multiple wavelengths. Recent observations using the Event Horizon Telescope have even captured the shadow of M87's black hole, providing a direct connection between the central engine and the jet. These observations have confirmed theoretical predictions about the role of magnetic fields in jet formation. Another compelling example is the Quasar 3C273, one of the brightest and most studied quasars in the sky. Its jet extends over 200,000 light-years and demonstrates the incredible power of relativistic jets to transport energy across intergalactic distances. The study of such systems has been instrumental in refining our understanding of jet physics and their broader impact on the universe. The study of black hole jets is not just about understanding individual galaxies. It also sheds light on the large-scale structure of the cosmos. Jets are thought to play a role in shaping the cosmic web, the vast network of filaments and voids that defines the large-scale distribution of matter in the universe. By redistributing energy and matter, jets influence the formation and evolution of galaxy clusters, helping to create the structures we observe today. Despite significant progress, many questions about black hole jets remain unanswered. For example, the exact mechanisms by which jets are launched and collimated are still a matter of active research. The role of magnetic fields, the nature of the particles in the jets, and the interplay between jets and their environments are all areas where theoretical models and observations are continually evolving. Magnetars and the extreme forces of magnetic fields in space. As a subclass of neutron stars, magnetars represent a rare and extreme phase of stellar evolution, pushing the boundaries of what we understand about matter and the forces that govern it. These enigmatic objects are fascinating not only for their unique properties, but also for the insights they provide into the interplay between gravity, magnetism, and quantum physics on cosmic scales. Magnetars originate from the cores of massive stars that explode as supernovae. When a massive star exhausts its nuclear fuel, its core collapses under gravity to form a neutron star, a compact remnant composed almost entirely of neutrons. Most neutron stars are already extraordinary, with densities so extreme that a single cubic centimeter would weigh more than 1 billion tons. However, a fraction of these neutron stars are born with rapid rotation and powerful magnetic fields, giving rise to magnetars. These magnetic fields can reach intensities of up to 1 quadrillion Gauss, or about 1 trillion times stronger than Earth's magnetic field, making magnetars the most magnetic objects in the known universe. The origin of these immense magnetic fields remains an open question, but several theories have been proposed. One hypothesis suggests that the intense fields are a result of a dynamo effect during the early life of the neutron star, where its rapid rotation and convection generate and amplify the magnetic field. Another theory posits that magnetars are born from progenitor stars with unusually strong magnetic fields, which are preserved and amplified during the core collapse. Observational evidence suggests that magnetars are more likely to form in environments with high stellar densities, such as star-forming regions, where massive stars are common. Magnetars exhibit a range of extraordinary phenomena, many of which are linked to their extreme magnetic fields. The immense magnetic pressure distorts the star's crust, creating enormous stresses that can lead to sudden shifts known as starquakes. These starquakes are analogous to earthquakes on Earth, but involve the cracking and shifting of a solid crust that encases an ultra-dense fluid interior. When a starquake occurs, it releases an enormous amount of energy, often observed as bursts of X-rays or gamma rays. These outbursts can last from fractions of a second to several minutes, depending on the scale of the crustal rupture. One of the most dramatic examples of magnetar activity is the giant flare. Giant flares are intense, short-lived emissions of gamma rays and X-rays that outshine all other sources in the galaxy for a brief moment. The energy released during a giant flare can be equivalent to what the sun emits over thousands of years. A famous example occurred in 2004 when the magnetar SGR 1806-20 produced a giant flare that was so powerful it disrupted Earth's ionosphere, despite being located about 50,000 light-years away. Such events are rare but provide invaluable data for studying the physics of magnetars and the behavior of matter under extreme conditions. In addition to flares, magnetars are also associated with persistent high-energy emissions. These emissions are thought to arise from the decay of their magnetic fields, which releases energy over time. As a magnetar's magnetic field decays, it heats the star's crust and powers continuous X-ray and gamma-ray radiation. This decay is not uniform and can lead to unpredictable changes in the magnetar's brightness and activity, making them dynamic and challenging objects to study. The magnetic fields of magnetars are so strong that they distort the very space around them, creating phenomena that challenge our understanding of quantum mechanics. In the presence of such intense fields, the behavior of light and matter deviates from standard physics. For example, in a process called vacuum birefringence, the strong magnetic field polarizes the vacuum itself, altering the way light propagates through it. Observations of this effect provide a rare opportunity to test quantum electrodynamics (QED) in extreme environments, pushing the limits of our theoretical models. Magnetars are also suspected to be linked to fast radio bursts (FRBs), mysterious millisecond-long bursts of radio waves detected from distant galaxies. Recent observations suggest that at least some FRBs originate from magnetars, as demonstrated by the detection of a bright FRB from a known magnetar in the Milky Way. If confirmed, this connection would provide critical insights into the mechanisms behind these enigmatic bursts, which have puzzled astronomers since their discovery. The study of magnetars has far-reaching implications for multiple fields of astrophysics. Their extreme magnetic fields and densities provide a natural laboratory for studying matter under conditions that cannot be replicated on Earth. For instance, the crust of a magnetar is believed to be composed of a highly ordered lattice of ions surrounded by a sea of degenerate electrons. Understanding how this exotic state of matter behaves under the stress of starquakes or magnetic field decay could reveal new physics about the behavior of matter at nuclear densities. Magnetars also offer clues about the life cycles of massive stars and the evolution of neutron stars. Not all neutron stars become magnetars. Most are observed as pulsars or remain dormant. The conditions that lead to the formation of a magnetar versus a pulsar are not fully understood, but they likely involve differences in rotation, magnetic field strength, and the environment in which the neutron star forms. By studying magnetars in various stages of their evolution, astronomers hope to uncover the factors that determine their unique properties. The environment surrounding magnetars is also of great interest. Their intense magnetic fields and high-energy emissions can influence the surrounding interstellar medium, creating shock waves, ionizing gas, and accelerating particles to near-light speeds. These interactions can produce nebulae akin to the pulsar wind nebulae seen around some neutron stars, but with distinct features related to the magnetar's unique properties. Observing magnetars poses significant challenges due to their variability and the difficulty of detecting their emissions across multiple wavelengths. Most magnetars are detected through their X-ray and gamma-ray emissions, requiring space-based observatories such as NASA's Chandra X-ray Observatory and ESA's XMM Newton, as well as radio telescopes. Cosmic voids are vast, nearly empty regions of space that account for a significant fraction of the observable universe. These structures, often spanning tens to hundreds of millions of light years, are the polar opposites of dense clusters of galaxies. While they may seem devoid of activity, voids are far from irrelevant. Their properties and evolution hold vital clues about the universe's large-scale structure, the behavior of dark energy, and the distribution of matter. Studying these immense cosmic deserts reveals as much about the formation and evolution of the cosmos as examining the galaxies and clusters that surround them. Voids are defined by their extreme underdensities, regions where the density of matter is significantly lower than the cosmic average. These areas contain fewer galaxies, stars, and dark matter compared to surrounding regions. However, they are not completely empty. Voids still harbor a tenuous mix of dark matter, diffuse gas, and isolated galaxies, often referred to as void galaxies. The distinct characteristics of these galaxies, along with the dynamics of matter within voids, provide a unique perspective on how cosmic structures evolve. The origins of cosmic voids are deeply tied to the early universe. Shortly after the Big Bang, the universe was nearly homogeneous, with tiny quantum fluctuations in density imprinted during the epoch of inflation. Over time, these fluctuations were amplified by gravity, causing denser regions to collapse and form galaxies and clusters, while less dense regions expanded, becoming voids. As matter flowed toward denser areas, voids were left behind, growing larger and emptier over billions of years. This expansion of voids is driven by a process known as gravitational evacuation. As matter is pulled into surrounding denser regions, the gravitational pull within the void diminishes, allowing it to expand at a faster rate than the denser areas of the universe. This expansion creates elongated and irregular shapes, often described as bubble-like structures. Adjacent voids can merge over time, forming larger void complexes, while their boundaries, known as filaments, become more defined. Despite their sparse nature, voids have a measurable impact on the large-scale structure of the universe. They are an integral component of the cosmic web, the intricate network of filaments, clusters, and voids that forms the universe's scaffolding. While filaments channel matter and galaxies into clusters, voids define the spaces between them, providing contrast and shaping the overall distribution of matter. Void galaxies, though few in number, are particularly intriguing. These galaxies often differ significantly from their counterparts in denser environments. For example, void galaxies tend to be isolated, less massive, and bluer in color, indicating ongoing star formation. This contrasts with galaxies in clusters, which are often redder and exhibit less star formation due to interactions with neighboring galaxies and the dense intercluster medium. The relative isolation of void galaxies protects them from these interactions, allowing their star formation to continue unimpeded. The gas within voids, known as the intergalactic medium, IGM, is also an important area of study. Though the IGM in voids is incredibly sparse, it still contains information about the composition and temperature of baryonic matter. Observations using the Lyman alpha forced absorption lines in the spectra of distant quasars, caused by hydrogen gas in the IGM, have revealed that voids are not entirely devoid of matter. These observations provide critical data for understanding the distribution of baryonic matter and the role of dark matter in structuring the universe. One of the most profound aspects of voids is their potential to probe dark energy, the mysterious force driving the accelerated expansion of the universe. Because voids expand more rapidly than denser regions, they are highly sensitive to the effects of dark energy. By studying the shapes, sizes, and growth rates of voids, astronomers can constrain the properties of dark energy and test cosmological models. Voids also amplify certain aspects of gravitational lensing, where the paths of light from distant galaxies are bent by the curvature of space-time. This amplification provides another method to study the distribution of matter and the influence of dark energy. The study of voids also provides a unique testing ground for alternative theories of gravity. In standard cosmology, gravity behaves according to Einstein's general theory of relativity, but voids offer environments with much weaker gravitational interactions compared to dense regions. Observing how matter behaves in these low-density environments can reveal deviations from general relativity, potentially pointing to new physics. Cosmic voids are identified and studied using large-scale surveys of galaxies, such as the Sloan Digital Sky Survey SDSS and the Dark Energy Survey DS. These surveys map the distribution of galaxies across the universe, allowing astronomers to identify underdense regions and measure their properties. Advanced techniques, such as three-dimensional reconstructions of the cosmic web, have improved our ability to detect and analyze voids. Future surveys, like those conducted by the Vera C. Rubin Observatory, promise even greater precision, enabling a more detailed exploration of void dynamics and their cosmological implications. Despite the progress made, many mysteries about voids remain. For instance, the detailed processes governing the formation and evolution of void galaxies are not fully understood. How do these galaxies acquire the gas needed for star formation in such sparse environments? What role do magnetic fields and cosmic rays play in shaping void dynamics? Addressing these questions requires both observational advancements and refined simulations that incorporate the full complexity of void physics. Another area of active research involves the role of voids in the distribution of dark matter. While dark matter is less concentrated in voids compared to filaments and clusters, it still exists and influences the motion of galaxies within these regions. Studying the gravitational effects of dark matter in voids can reveal its properties, including its interactions with baryonic matter and its contribution to the overall structure of the universe. Our universe is just one of countless others, each with its own physical laws and properties. If true, the end of our universe might be part of a larger cosmic cycle, with new universes continuously forming in an infinite multiverse. This idea is often tied to theories of eternal inflation, where regions of space-time undergo perpetual expansion, spawning bubble universes with diverse characteristics. Another speculative concept involves the possibility of quantum rebirth, or the emergence of new universes from black holes. Some theories suggest that the singularities within black holes could give rise to new regions of space-time, effectively creating baby universes. If this is the case, black holes could serve as cosmic seeds, perpetuating the cycle of creation even as our own universe winds down. The question of what lies beyond the end of the universe is not just a scientific one, but also a philosophical and existential inquiry. Does the universe have an ultimate purpose, or is its end simply a consequence of physical laws? Can life, intelligence, or consciousness persist in some form, even as the cosmos fades into darkness? These questions challenge the boundaries of human understanding and inspire contemplation about the nature of reality and our place within it. Advances in observational astronomy and theoretical physics continue to refine our predictions about the universe's fate. Projects such as the James Webb Space Telescope, the Square Kilometer Array, and next-generation gravitational wave detectors will provide new insights into the behavior of dark energy, the properties of black holes, and the structure of space-time. These discoveries may reveal whether the universe will freeze, rip apart, or collapse, offering a clearer picture of its ultimate destiny. The end of the universe, whether gradual or sudden, is a reminder of the transient nature of all things. It underscores the vast scales of time and space that define the cosmos and challenges us to appreciate the fleeting era of light, warmth, and activity in which we live. Even as we look toward the distant future, the mysteries of the universe's end continue to inspire wonder, curiosity, and the search for understanding. That's the end of this video. Make sure to subscribe, and if you want to watch more content like this, check out our channel.